Okay, we're talking about DNA replication, and your task here is to determine which strand will be your leading and which strand will be your lagging strand. So you've been presented with the DNA molecule, and initiator proteins have initiated the replication process by separating the strands, recruiting helicase, DNA polymerase, primase to the scene. So now we're going to look at the bubble that has formed, and we're going to consider this or call this as origin of replication. So it means this is the region where we're going to open it up, and based on these two parental templates, we're going to build complementary strands. So this is my replication bubble. That means this is the origin of replication. This is where we're going to initiate a bidirectional replication process. Let's assume you have been given at least one prime end of your DNA strands. So let's say this is your 3' end. You know the other end therefore is going to be 5' end. And since strands are antiparallel, the other strand will have to be, or will have to have a 5' end, and this will be your 3' end. So now these two strands will serve as your template strands, and you're going to build a complementary strand based on each template. So where do we begin? So first, what you need to do is visualize where those complementary strands are going to be sitting. So if the top strand is my parental strand, the strand that I'm about to build is going to have a 5' end. And I'm going to put the dots to represent where the strand eventually be located. So notice this end will have to be 3, and the same for the other template strand. So if this is 5, this will have to be 3, and the strand we're going to build will be sitting right here. Okay, and this is going to be your 5' end. And notice that each resulting DNA molecule from this replication process will have a template strand, that original parental strand, and also a complementary strand. So that means it will be half old and half new. Next, we want to address or separate this bubble into two parts and address each part separately. Because remember, the process of replication is bidirectional. So we have the overall synthesis of complementary strands moving in two opposite directions. Let's go ahead and separate the bubble in half so we can address each part separately. So one thing to keep in mind is that DNA polymerase can only build or elongate a complementary strand in the direction of 5 to 3. Even though it cannot initiate synthesis at the 5' end, and it needs the help of the primase to lay down the primer first, that's going to offer the OH group in order for the new nucleotide to be added. So, but once we have that, DNA polymerase will be able to build a strand in the direction of 5 to 3. So again, the 3' end at this point will offer an OH group, and therefore new nucleotides will be added on to that end. So what you want to do is figure out, remember we're going to be looking at each half of the bubble separately. So you want to label your complementary strand ends first. Since this is your 5' end, the other end that you're going to have to build is going to be 3 right here. And then the opposite strand, since this is your 3, this end will have to be 5. So now from this point on, all you have to do is apply this rule. The fact that you can build a complementary strand in only this direction. You can only go from 5 to 3. Now remember, assuming you already have your primers there as starting points. So if we start right here at the origin of replication and overall direction, we're moving to the left at this point. If we look at the top strand, top complementary strand, this is a 3' end. So it means we cannot initiate synthesis right here. However, if you look at the opposite strand, we actually can, because this is our 5' end, and assuming the primer is already there, DNA polymerase will be able to immediately add the nucleotides in this continuous fashion, following the helicase. So this strand right here becomes your leading strand. Because we're going from 5 to 3, we are following the rule. So your other strand will have to be built in fragments called Okazaki fragments, because notice we cannot initiate synthesis at the 3' end. We can only add nucleotides to the 3' end. So it means we have to build the strand in fragments. So as soon as the helicase opens up the parental strand, we are going to make the first fragment. Notice in the direction I'm moving, because I'm going from 5' end overall to the 3. So this is going to be your first fragment. And now we open up more, we make the second fragment, we open up more, we make the third fragment, and we continue on building the strand in fragments. We're going to call it a lagging strand. So now all we have to do is do the same for the other side of the bubble. So if this was my 3' end, notice the other end has to be 5' end. And if this is 5, this has to be 3. So how are we going to build a strand? Which is going to be your leading and which is going to be your lagging? What do you think? Apply this rule. So we go from 5 to 3. So it means, all right, we can build a strand in the direction of 5 to 3 nice and continuously. So this becomes your leading strand, and the other strand is going to be your 5 to 3, 5 to 3, 5 to 3, fragment 1, fragment 2, fragment 3. That means this is your lagging strand. So then you wonder, hey, what's going on right here? How come we have, is there a gap in between the two? No, there isn't, because remember we have a phosphodiester bond right here between a 3' and sugar molecule and an oxygen in the phosphate group, which is that 5' end of the nucleotide. So they have a bond there as well. So I want to go back and quickly address the situation with the primers, because remember primers were needed in order to initiate the synthesis to help DNA polymerase build the strand. So if we look at the leading strand, we only needed to lay down a primer once. So this was your primer here, and then extension took place. That was carried out by DNA polymerase. On the lagging strand, every time we built a fragment, we had to lay down a primer. So it means we had a primer here, and here, and here. And then on the other side of the bubble, the same thing. The leading strand had a primer right here to initiate the synthesis, and on each fragment in the lagging strand. So here, and here, and here. And remember, these primers do not stay within the DNA molecule. DNA polymerase will remove those primers, replace them with DNA nucleotides. Bonds are going to be formed in between those nucleotides, and the ligase is the one that's going to do the job. Okay, so whether or not you've been given a full bubble or half the bubble, remember to apply this rule and you'll be good.